Hello everyone, in this talk I will introduce our paper FreeTensor, a free-form DSL with holistic optimization for irregular tensor programs. I'm Shizhi Tang and we are from Tsinghua University. Tensors are multidimensional arrays, for example scalars, vectors, and matrices. Tensors are core data types in many applications, ranging from deep learning, scientific computing, or computer graphics. To ease programming, many tensor programming frameworks are widely in use. These frameworks are originally designed for deep learning, but also in use in many other fields. Tensor frameworks provide two critical features. First, they can run tensor programs in many kinds of devices, from multi-thread CPUs to GPUs. Second, they can be used for automatic differentiation, or AD, which is necessary in many cases, for example, to train a deep learning model. Currently, most tensor frameworks are designed in an operator-based manner. Users need to train tensor operators as a graph to form a program. This is a good choice to run on devices and apply AD for classic deep learning models, which are regularly layer by layer, and each layer can be expressed as several operations. However, there are many other programs that are not regular. These programs are no longer typical layers, and they may contain complex workflows such as control flows or random indexing. For example, there are emerging deep learning models that implement their own customizations on convolution or transformer layer. And there are also programs dealing with irregular objects by nature, such as 3D objects or physical environments. These are challenges for operator-based frameworks. Let's have a close look at a detailed example, SubDeepNet, which is a convolution neural network for 3D objects represented in meshes. For example, here's a ball represented in a mesh, or it can be shown in a 2D form like this. We need to compute this formula as one of the SubDeepNet layers, and there's a sub-expression in a red box. To compute this sub-expression, we need to find 3 adjacent faces for each center face, and compute an absolute value of the difference of each 2 adjacent faces in a circular manner. In an operator-based framework, we need to express this procedure as tensor operators. Please remember each tensor operation operates on the whole tensor. Therefore, we need to pick the left neighbors of all faces as a new tensor, and the right neighbors, then the upper neighbors. Next, we put these 3 tensors together as a new tensor and repeat this procedure in a different order. Next, we compute the absolute value of the differences on these 2 tensors and sum it over a dimension and multiply it by a weight matrix, and finally we get the result. In this example, we apply each operator on a whole tensor, which leads to redundant memory access, pool cache access pattern, and extra kernel launch if we are using a GPU, and they all contribute to performance overhead. Instead, in FreeTensor, we support programming directly with conventional loops. We loop over all faces, and then loop over all its neighbors, and directly compute the circular difference. Finally, we multiply the result by a weight matrix and store it back. There are already some existing works on introducing more expressiveness in complement to tensor operators. JAX and PyTorch provide a new meta operator named remap, which can be viewed as a dependence-free loops around one or more other operators. TVM supports customize the operator as a perfect loop nest. Recently, TVM releases a new extension named TensorIR, which supports more customizations as blocks. However, there are still many programs cannot be expressed by these restricted loops. In FreeTensor, we further extended the expressiveness of tensor programs. Particularly, we support non-perfect loop nests and loops with dependencies. To achieve this, FreeTensor provides an embedded Python DSL to write a tensor program and an optimizing compiler to compile it to native code. In this talk, I will first briefly introduce our DSL and compiler, and then highlight 3 key designs in FreeTensor. First, I will briefly introduce our embedded Python DSL. Tensor programs in FreeTensor are written in our DSL. Here is a minimal example of a vector addition. We first define a DSL function, vadd. The tensor types of the parameters and the return values should be defined. Next, we look over all elements in the tensor to do the addition. Finally, we mark the function with an decorator, calling FreeTensor to compile and optimize it. In our DSL, we support tensors as first-class citizens. Loops and branches are supported in our DSL and will be compiled to native code, including a parallelized one. Traditional tensor operators are still supported, and they can be called even inside a loop. They will be inlined to enjoy a joint optimization. Next, I will briefly introduce our compiling workflow. Our compiler runs as a Python library. We pass the AST of user function in our DSL to build our own intermediate representation, or IR. Our IR is also in an AST form. If needed, we apply automatic differentiation on our IR. After that, we apply a series of optimizing transformations and lowering passes on the IR. Then we generate native code to compile it. Finally, we load it back to Python and execute it. From the user's perspective, all of this happens as a Python library. In the following part of this talk, I will introduce 3 key designs in FreeTensor. The first is how we support generic operations in our Python DSL. It's common to write a program that supports any number of dimensions. For example, a tensor addition function that can be used for scalars, vectors, matrices, and other tensors. Here is an example of the add function for 3D tensors. We loop along all the 3 dimensions and do the addition. But how should we support any number of dimensions? There are some traditional solutions, but they introduces too many indirect indexing, which leads to performance overhead. In FreeTensor, we solve the problem by supporting a program with finite recursions and compile it by partial evaluation to achieve both granularity and performance. Suppose the number of dimensions is known at compile time. We take 3D tensors as an example. We can write a recursion where each stack frame loops along one dimension. At the outermost stack frame, our compiler will check the exit condition and find it always false. So we can remove the dead branch and leave the else case only. Then we can inline the next stack frame and keep removing dead branches. We repeat this procedure until the function is fully inlined, and we'll get the loop-based program just like what we will write. Our second highlight is on how we deal with dependencies in loops when we are applying optimizations. To run a tensor program on all kinds of devices, architecture-dependent optimizations are critical. Since Halide, the idea of separating a program as an algorithm and some transformations or so-called schedules is proved to be a good practice, we borrow it to FreeTensor. However, dependencies inside a loop may lead a transformation wrong. For example, we can apply a transformation to reorder these 2 loops in figure A, but we cannot do this for figure B because there is a dependence. We make use of polyhedral analysis to analyze the dependencies in a program to apply safe transformations. Polyhedral analysis is a well-established theory for dependence analysis. In short, the dependencies are represented by integer sets and their mappings, which can be solved mathematically. We support various transformations in FreeTensor. For example, the split transformation splits a loop into 2 nested loops. In FreeTensor, we use the ISL library to analyze for these transformations. You can read our paper for more detail. These transformations can be applied by users explicitly or can be done automatically using our built-in heuristics. Our third highlight is on how we support automatic differentiation, or AD, on irregular programs. In a traditional operator-based framework, AD is easy. It just reverses the operator graph to form a gradient graph. But for irregular programs, we need to rewrite the program as a gradient program. Works including Enzyme and Zgold have already supported AD for an irregular program. However, there are still some performance issues, especially how to reuse intermediate variables efficiently. Let's have a look at this example. Here is an intermediate variable t, and it is used to compute the output tensor y and z. In a gradient program, we have to reuse the value of t. We have two choices. One is to store the value of t in all the iterations in a large tensor, or so-called tape, and load it back in the gradient program. Otherwise, we can recompute t in the gradient program instead. There is a performance trade-off between these two choices. Storing t requires a large tape tensor, which leads to performance overhead. Remember, the reason that we want to avoid pure operators is to avoid large tensors. In the worst case, storing all intermediate variables will wipe out all the advantages of operators. But recomputing t requires extra computation, of course. Our strategy in FreeTensor is to recompute the tensors that are reused in the original program only, which require more spaces to store. We find out these tensors by already described polyhedral analysis. Finally, we evaluate the performance of FreeTensor. We compare with 5 baselines. PyTorch, JAX, and TVM are operator-based frameworks. As described, they also provide some degree of customizability other than pure operators. Julia is the general-purpose programming language, which is mainly designed for tensor computations. DGL is a specialized framework for graph neural networks, which is one of our test cases. We evaluate FreeTensor with subprograms from 4 applications. SubDeepNet is a CNN model for 3D objects. Longformer is a transformer model customized for long sequences. SoftRAS is a differential graphic renderer, and GAT is the graph neural network. We evaluate FreeTensor both on CPUs and GPUs. This is our end-to-end performance without AD. We achieve up to 5.10-fold speedup over the best baseline. When running with AD, we achieved up to 127-fold speedup thanks to our strategy for AD. We further analyze the reason of our speedup. Experiment shows with a similar amount of computation, FreeTensor can significantly reduce the number of GPU kernels and GPU memory access. Finally, we analyze the performance of AD. Comparing with storing all intermediate variables, our strategy contributes to up to 6.83-fold speedup. In this talk, we introduce FreeTensor, which is our language and compiler for writing irregular tensor programs in loops, instead of pure tensor operators. FreeTensor compiles an embedded Python DSL to native code and optimizes the programs with dependence array transformations, and we have AD support with performance considerations. FreeTensor is now open source at this GitHub repo. And finally, thank you for watching. Questions are welcome.
So you said you use polyhedral analysis to check for dependence, right? So
yes.
If there's any sparse tensor computations that are happening, like how do you do this?
Yes, we support random access or access by loop iterators. If the indices are loop iterators, we can accurately analyze it by polyhedral model. But if they are sparse programs, they can be arbitrary inputs. So we have to relax the conditions, and the polyhedral model may not be able to give an accurate answer, and we will have to fall back to a safe analysis. That is, we won't result in a wrong program, but some transformations may not be able to perform.
Okay. So did you find any problems when you are evaluating against graph neural networks, for instance?
Sorry, can you repeat?
Sorry. So So I see like that here evaluated against like graph attention networks, if I'm not mistaken.
Yes.
Yeah. So did you find any problems in dependency analysis there?
Well, we support graph attention network. That is a sparse program, but we don't have to schedule the loops which are sparse accessing. We parallelize the loops we can parallel, so the program can be optimized. Further, we support some user hint on the program. They can hint a loop to be dependency free, so it helps make further transformations.
Great, thanks. All right, so I guess like that's all. So thank you very much, Rishi, for the talk.
And thank you for your questions.